My name's Chris Tallickson. I'm with the Utah Office of Energy Development, and I'm the moderator today, holding up cards to keep the speakers in line. We're on track with our technology, so I'm going to proceed into the introduction of our first speaker. Anthony Turhallow actually lives in the Logan area and is based on the Utah State campus, correct? No?
Out of my house.
Oh, out of his house. Sorry. Well, he's an economist with the Oak Ridge National Lab. He has a PhD in agricultural economics from Iowa State. And he was a contributing author to the original billion-ton biomass resource study published in 2005, and also a contributor to the recent update to that report, which will be the topic for his presentation. So without further delay, I'll introduce Anthony Turhallow.
In 2005, Department of Energy published a study showing that it was possible to supply 1 billion tons of biomass in the United States. The genesis for that 1 billion-ton number was the Department of Energy has a research program in biomass for energy, primarily in various conversion processes. So they were looking to justify their conversion program, and they wanted to make sure that there was enough feedstock available to justify the fact they were spending money on conversion research. And so they set a goal, well, can we replace 30% of the liquid transportation fuels used in the United States? And to do that, you would need about 1 billion dry tons of biomass available. So starting somewhere around 2002, 2003, Oak Ridge National Laboratory and a lot of other collaborators started on a study. It was published in 2005, and it showed that, in fact, you could, there were 1 billion tons plus of biomass that could be available. The 2005 study was really, is the biomass there? It didn't incorporate economics, it didn't incorporate sustainability criteria. And the 2011 update, part of what it did was correct some of these deficiencies in the 2005 study, incorporating sustainability criteria as well as estimating supply curves for biomass, various biomass resources. In this, in the 2011 billion-ton study, the resource base includes about half the land in the continental United States. So it includes both forest resources as well as agricultural resources. It's fairly comprehensive in what it includes in the various categories in both the agricultural area as well as the forestry area. So resources that are currently available, such as crop residues, corn that's presently used to produce ethanol, animal manures, various processing residues, such as from grain milling, as well as municipal solid waste, both the woody component as well as the non-woody component. For the 2011 study, we also added an annual energy crop into it, in addition to the perennial energy crops that were looked at in the 2005 study. One of the questions we get periodically is algae included? And the answer to that is no, it is not included. One of the improvements in the 2011 study is we were estimating our supply curves at the county level, whereas the 2005 study was at national level. So the 2011 study should actually be a lot more useful to people who want to possibly look at feasibility studies, because it does have data by the county level. There are, the Department of Energy did produce an algal biofuels roadmap, and there's a citation up there. And there also has been an assessment of the potential of algae. And I suppose if we do a billion-ton update 3, we may in fact get into algae, but that would be a number of that would be a number of years from now before we probably do another update. In the study, there are two different scenarios. One is a baseline scenario, and another one is a high-yield scenario, in which the high-yield scenario, research and development of biomass resources is a lot more aggressive than in the baseline. The study goes out to 2030, and to show you, kind of give you an idea of the difference between what's happening in the baseline and in the high-yield scenario. Right now, national average corn yields are about 160 bushels an acre. And in the baseline, we estimate it would be about 201 bushels per acre in 2030. And that's based on USDA estimates out to 2020 that are then extended. And the high yield is 265 bushels per acre. So you could see that's an increase of about 60% over what we're doing now. So that's quite an increase in corn yield. And one of the byproducts, of course, of corn potentially is corn stover, the residue from the crop. So you can see if the yield, in fact, went up 265 versus 160, your total amount of residue actually goes up quite substantially. In the residue, crop residues are one of the potential sources, and in our study, we assumed that you could only collect those from acres that are either have no tillage or reduced tillage practices. If it's conventional tillage, then we assumed that no residue could be collected. And so one of the differences between the high yield scenario and the baseline is that we assumed that there was a greater shift over time toward the no-till and reduced tillage, which again allows more residue to be collected. The energy crop yields, so the energy crops were short rotation woody crops, which would be things like poplar, willow, eucalypts. On the agricultural side, there would be things such as switchgrass, miscanthus, energy sorghum. So in the baseline, we assume the energy crop yields increase at 1% per year. But in the high yield scenarios, we looked at three different levels, 2%, 3%, and 4%. And over a 20-year period, which would be from 2010 to 2030, if you assume that the energy crop yields increased at 4% per year, you would actually be doubling the yield, almost doubling the yield of the energy crops, which is quite a significant difference. And the 4% would have to be quite aggressive research. For agricultural crop residues, in the baseline scenario, let me back up a minute here. In the 2011 update, we incorporated sustainability requirements that were not in the 2005 study. And so these included, you had to maintain soil carbon, and erosion on the land on which you remove the residue could not exceed the threshold, the T value as USDA calls it. In the baseline scenario, there were about 111 million dry tons and mostly corn stover, and by 2030 that had increased to almost 183 million dry tons. In the high yield scenario, the total residues from crop residues increased to 320 million dry tons, which is a significant increase over the 2012 level. For potential forest biomass and wood wastes for 2012, you will notice that no single category is big and that there were only modest increases in the quantities with price. You'll also note, if you look at the bottom two lines, we did the study both with and without federal lands. And with federal lands and without, the difference is actually very minor. One thing that you can see from this graph for energy crops is that price makes a difference. You can see that at $40 a dry ton, you have very limited amounts of energy crops coming in, but if you increase the price to $60 per dry ton, and if you look out at 2030 in the baseline, I mean, you're over 300 million dry tons. And if you, in fact, look at the high yield, where the yields increase quite a bit more, then you're up to almost 800 million dry tons. So one of the things is that, one of the take-home messages is that price matters. And the energy crops had to compete with conventional food and forage crops. And that was done within an agricultural modeling framework, the polysys model. And what happened is that at relatively low prices, some cropland was converted into energy crops, whereas at the higher prices and out further in time, a lot more pasture land was converted into energy crops. What this map shows is where crop residues and energy crops were potentially available, and it makes sense that it's where you have your major agricultural production, basically in the Midwest, in the Southern Plains, in the Northern Great Plains, and lesser amounts in the Southeast. And with forest residues, again, it's where your forests lie in the western United States, as well as in the Southeast, and some amounts in the northern tier of states. And this map shows just all potential categories of feedstocks, and you can see that the southern plains, the northern plains, that the quantities by state are quite large, and then you have significant amounts as well in the Southeast, as well as in the Corn Belt. And you'll just notice that different regions are dominated by different types of feedstocks. This map, as the color gets darker, shows the density of potential resources by county. And you can see that in Kansas, for example, that's where we actually show the most dense resources available. If I may summarize, in comparison with the 2005 billion-ton study, the 2011 study is on the same order of magnitude. There are some differences. You can look at the graph at the bottom, and you can see that in the 2005 study, the moderate, and the 2011 baseline, those are kind of equivalent. There's a little bit of difference, and you'll notice shifts. The amount of crop residues has gone down, and that's because the sustainability constraints were incorporated in the 2011 study. Forest residues are slightly less because of the decline in the forest products industry. And energy crop potential is greater. Part of that was because we added the potential to use pasture land to convert into energy crops. And we also actually did a modeling exercise with the polysys model, where we actually could allow energy crops to compete with conventional crops. In 2030, the range of biomass feedstock resources ranges from 1.1 to 1.6 billion dry tons at $60 per dry ton. So this does in fact meet the Department of Energy's desire to have at least a billion dry tons of biomass resources. A significant amount of what we estimate is actually in what we would call current used categories of resources, such as grain for ethanol, soy oil for biodiesel, as well as some of the forest resources, fuel wood, some of the processing wastes. If you want to read the whole report, it can be downloaded at this website. And one of the things that has been done as well is a lot of the data from the report has been loaded onto another website. It's known as a KDF, which is supposed to be, it stands for the Knowledge Discovery Framework. And a lot of the data is available there, and that's a work in progress. So over time, more and more of the data from the study is being put onto that website. I have tried to go into that website a couple of times, and I have some challenges in finding what I want to find. So I think it'll get better over time, though.